start. Uh, so we will start chapter 9.6, section 6, Taylor and Maclaurin series. Well, actually, we have seen so far several functions that has power series expansions. If a function has a power series expansion which is valid on some interval, then we will call that series a Taylor series or the Taylor series of the function. Okay, so that series will be called the Taylor series of the function. But before I gave that definition, there is this easy observation. Let us first see that. Now, suppose the series f of x a n x minus c to the power n, which is just a0 a1 x minus c a2 x minus c squared an x minus c to the power n converges to f of x. Of course, when I write it like this, it is already right. It suggests that f of x is equal to this. Therefore, this state is convergent to f of x. But nevertheless, we say it again for c minus r x c plus r, where r is a positive number. So suppose that f of x has a power series expansion like this, and this power series expansion is valid on an interval like this. Okay, so you go r units in both ways. So this is c plus r, c minus r. Suppose we have some interval like this where this representation is valid. Then the conclusion is this. Then I know that this function is differentiable, but we have this. Then ak, so the k term here is nothing but the kth derivative of f evaluated at c divided by k factorial for k equals 0, 1, 2, and so on for all k. So that's the theorem. And this is easy. I mean, we have every tool to show this. Well, f of x is equal to this, a0 plus a1 x minus c, a2 x minus c squared, a n x minus c to the power and so on. And this is true for all numbers between c plus r and c minus r, right? Well, if this is the case, then its derivative is what? Its derivative is just a1, right? Plus 2a2 x minus c squared and so on. Here I have n times a n x minus c to the power n minus 1. This is also true for all x between c plus r and c minus r. I can take second derivative. What will be the second derivative? Şurada yanlış yapmışım değil mi ben? Şurası olmayacak. Okay. Second derivative is just 2a2 plus 6 6a3 x minus c, and so on up to n times n minus 1 x minus c n minus 2, and so on for x again between c minus r and c plus r. And if you keep doing this, let's say, what is the kth derivative? Bakalım. Sıfırıncı terim, zero derivative starts with, right? Zero derivative means you don't take the derivative. So it starts with a0. First derivative starts with a1 and then a2. It will be a3 and so on. And what is the coefficient here? So you see each time the power comes down, the coefficient here 1, so it is 0 factorial times a0. Here 1 factorial times 1, 1 factorial times a1. This is 2 factorial times a2. Next one will be 3 factorial times a3, right, which is 6, and so on. And this will be just uh, k factorial times uh, ak plus okay, what will be the next? K artı 1'in so it will be just k plus 1, k, k minus 1 up to uh, 2, here x minus c to the power 1, and it will go like this. What about this term? So you take derivative k times, so it will be n times n minus 1, n minus 2, n minus her k defa türev aldığınızda n eksi k gelecek. Ama burada n eksi k artı 1 var. X minus c n minus k plus da da da da. Okay. So we have all these. Now plug x equals c in all uh, lines. Şimdi if I plug x equals c here, I get what? I have c minus c, which is 0. C minus c is 0. So all these terms are 0. What is left? Only a0. So when I plug 0 here, c here, I get just a0. So f of c is just a0. What about the second one? When I plug c here, I get c here, c minus c, which is 0, 0, 0. I just get a1. So f prime, this is just a1. F double prime c is just what? Double prime de koyduğumuz zaman this is 0, this is 0, and so on. So this is just 2a2, 2a2. And here kth derivative, when you plug x equals c, I get k factorial times a to the power k plus 0, 0, 0. So I have only these. Therefore, ak is just kth derivative of f evaluated at c equals k factorial. Okay, so this proves the result. So if you have a function given as a power series, has a representation, power series representation, then these coefficients are nothing but basically the derivatives of f uh, evaluated at c. Sorusu olan var mı? Bir kere daha tekrar edeyim. Aranızda METU Class'a üye olmayanlar varsa Gökhan, Benli'ye so those who are not registered in METU Class yet should just send a message to Benli at METU Edu TR using your METU account, okay? Okay. And follow the Math120 page, okay, for information about the exam, where you will take the exam and so on. Okay. Definition. So if f of x has derivatives of all orders at x equals c, then the series so you just compute these derivatives, divide by k factorial. So this is like an or ak, x minus c to the power k, k from 0 to infinity, right? Here, this is just this ak. If the function has a power series representation, uh, but this definition is independent from the above considerations. Here, I just take a function so that its derivative exists at all at the point C, right? All the derivatives exist at a single point C. Then we form this sequence, this series, power series, and we will call this. So what is this? This is of course f of c. When you plug 0 here, you get just x minus c to the power 0, which is just 1. 0 derivative is just f. 0 factorial is just 1. Therefore, the 0th term is just this. And then the first derivative divided by 1 factorial x minus c. Second derivative x minus c squared over 2 factorial. And keep going like this. Kth derivative divided by k factorial x minus c to the power k and so on. Then this series is called the Taylor series of f about x equals c. If c equals 0, then the term Maclaurin series is usually used in place of Taylor series. Yani Maclaurin serisi Taylor serisi, başka bir şey değil ama Eğer e, interval yani türevler sıfır noktasında alınmışsa. O zaman ona Taylor serisi demiyoruz da Maclaurin serisi diyoruz. So when if you take the derivatives at zero, then the series you get is not called usually Taylor series. It has a special name. It is called Maclaurin series. Okay, but it is the same thing, of course. So far, this is just the definition. Another definition. Analytic functions. A function f is analytic at C if f has a Taylor series at C and that çok yaşa that series converges to f of x in an open interval containing C. If f is analytic at each point of an open interval, then we say it is analytic on that interval. Anlaşıldı mı bu? Pek değil mi? Yani ne söylediği belli değil. Okay, let me explain what analytic means. Suppose you have a function f of x, okay, and you form also, suppose this has derivatives of all orders at the point C, so you can form its Taylor series, which is just kth derivative at C divided by k factorial x minus C to the power k. So you have this function, and using that function you form another function, this Taylor series of f. In general, these two gadgets may not be equal to each other, okay? We will see examples. So a function may not be equal to its Taylor series expansion. If this is convergent to this, so if these are equal, then we say that f is analytic at the point C, okay? Suppose we have an interval like this. If it is convergent on this interval to this function, then it doesn't matter how big or small this interval is. If there is an interval like this, so that this power series is convergent to f of x for all x in this interval, then we say that f is analytic, okay? Why these are important? You see, why this is a great thing for a function. All these coefficients are computed at a single point, at the point C, right? But then you can plug any number you want in this interval and you compute this function from this object, right? The coefficients are computed at a single point, but it determines the values of the function on the whole interval. So knowing the function at a single point, but I mean knowing the function and all of its derivatives at a single point enables you to determine the function on the whole interval. If your function is like this, then it's a very special function and we call it an analytic function. Okay, that's why they are important. They are of course differentiable functions, but they are much more than differentiable. There are differentiable functions which do not satisfy this equality. Okay, so analytic functions are very special functions. Analytic functions are like extensions of polynomial. It's not, it's like a polynomial, but it's an infinite polynomial. Okay. Uh, okay. If it is analytic at all points, then we just say that it is analytic on the whole interval. Okay. Now let's see some examples. Okay. What we mean by elementary functions, usually the functions that has, you know, some well-known names like polynomials, exponential, trigonometric functions, logarithms. Okay, these are elementary functions. Of course, there are many other functions. Actually, uh, most of the functions doesn't have a name. Okay, because they are just too many. Names are also, we have infinite many names, right? A1, A2, A3, right? You can call them like this, infinitely many, but the space of functions is much bigger, so that a function usually cannot have a, you know, name. The names are limited. Reel sayılar da öyledir. Yani reel sayılar sonsuz tane. Her reel sayının bir ismi olamaz. Çünkü isimlerin sayısı countable'dır. Sayabilirsiniz. The number of names in an alphabet is a countable set. You can count them. Okay, but real numbers is uncountable. Therefore, just few real numbers has a name. The others doesn't have a name. Okay, functions are also like this. We know many functions, but in the space of all functions, they occupy a very small place. Okay, I can tell you that if you pick up a function, that function, for that function to be a elementary function, something we already know, the probability is 0. Okay, so but usually, you know, when I ask you tell me a function, you of course say a function which is something familiar, right? But the place they occupy in the space of all functions is kind of measure 0. Okay. Okay, now let's write down or find the Taylor series of f of x, which is e to the power x. Well, this is easy because derivatives are easy, right? It is differentiable everywhere, and moreover, the kth derivative of this is what? Well, it is still e to the power x. So kth derivative of this at c is e to the power c. Okay. Uh, so the Taylor series of e to the power x about x equals c is what? What is the Taylor series? Taylor series is this. You compute the derivatives at c, divide it by k factorial, and then multiply by x minus c to the power k, k from 0 to infinity. So this is just e to the power c times this x minus c to the power k, k from 0 to infinity. E to the power c is common in all terms. It's a fixed number. I can just take away it from the summation and write this. X minus c to the power k divided by k factorial. Okay? Okay. Now let's also find uh, or let's determine if it is convergent. Convergent. Uh, where it is analytic. And okay. Peki. Şimdi I have this power series e to the power c. Uh, I can write it for n, right? Let me write it like this. N factorial x minus c to the power n. How can we find the radius of convergence? We have to write down what is an for this, right? An is just this is a power series. An is the coefficient of x minus c to the power n. So it is just e to the power c n factorial. So L was limit an plus 1 over an as n goes to infinity if the limit exists. Let's see if it exists. An plus 1 is e to the power c n plus 1 factorial divided by an is just n factorial times over e to the power c. Well, there are some cancellations here, right? This is cancelled with this one, n factorial is cancelled with this. Only limit 1 over n plus 1 is left, and this limit is 0. So L is 0, hence the radius of convergence is 1 over L. Since L is 0, it is infinite, okay? So radius of convergence is infinite. Therefore, the series is convergent on the whole real line. Hence, the series converges for all x, okay? For all x. Okay. Now, suppose that since it is convergent, g of x is this gadget, okay, e to the power c and factorial x minus c to the power n, okay. Uh, okay. This is, of course, this power series is convergent for all x, right? So I know that I can integrate or differentiate this gadget. Let's take the derivative. Then the derivative of this is what? Derivative of this is just n from 0 to infinity e to the power c n factorial and then n times x minus c to the power n minus 1. But what is this? İsterseniz şöyle yapayım. Let me write it this way. It is easier. Then x is just when n equals 0, you get e to the power c, and then e to the power c over 1 factorial x minus c, e to the power c over 2 factorial x minus 2 squared, e to the power c 3 factorial x minus c cubed, and so on. So when you take derivative, you get 0 and then e to the power c plus 2 comes down and you get just e to the power c x minus c, and then 3 comes down and you get e to the power c 2 factorial x minus c squared, and then I have here e to the power c over 4 factorial times x minus c to the power 4. When you take the derivative, 4 comes down and 4 factorial becomes 3 factorial. So the next term is just e to the power c 3 factorial x minus c cubed, and so on. Well, what you see is just the same function. So this is again gx, right? When you take the derivative of this expression, you get the same thing back. Therefore, hence, thus, g of x satisfies the differential equation. Well, you don't know what it is, but differential equation y prime equals y. Okay. And from the theory of differential equations, if you have a function like this, it should be exponential. The you will see this next year, I mean in the fall, in 2019. Then the theory of differential equations tells us that g of x is indeed e to the power x. Dolayısıyla da şunu görmüş oluyoruz. So we have this e to the power x is equal to its Taylor series about c. Okay, and this is true for all x. Therefore, so this function was so this was g, but differential equations, this theory tells us that this function should be e to the power x. So e to the power x is equal to its Taylor series, and this means what? In particular, particular e to the power x is analytic on the whole real line. Değil mi? E üzeri x Taylor serisine eşit. Bütün real eksende ve e, Taylor serisini de istediğiniz nokta etrafında alabiliyorsunuz. Hani sıfırda da alabilirsiniz. 1'de de 2'de de. Mesela Maclaurin serisi ne olacak? The Maclaurin series for e to the power x is what? Ne yapacağız? C yerine 0 yazıyoruz. Right? This is just c equals 0. When you plug c equals 0, e to the power 0 is just 1. So 1 over n factorial x to the power n. And from 0 to infinity. Now it is easier to see that when you take derivative, you just get e to the power x, right? I mean, its derivative is equal to itself. Okay. Find neyse sonraki örnekleri yarın yapayım. Bir şeyi söylemeyi unutmuşum size. Alternating series testte bir error hesabı var. Genelde onları arkadaşlar yapmıyoruz demişlerdi ama alternating series test için yapılıyormuş. Ben bu dersi 15 yıldır vermedim. O yüzden hani o şeylerde biraz sıkıntım var. Neyi ne kadar yapacağız? Ya ben kalkülüs verdiğim zamanlarda bu ders yoktu zaten. Başka kodla veriliyordu falan. İçeriği çok değişti. Arkadaşlar bana hatırlattılar. So let me just give you that gadget which is included apparently in the syllabus, but I forgot to tell you before. So I'll continue this series stuff tomorrow, but for now, let me just do this. Error estimation for alternating series. Okay. Now, suppose that an is an alternating series, is a convergent, is an alternating series which is convergent by ACT. Yani ACT'nin koşullarını sağlasın. Bu ne demek? So işte an plus 1 is all negative for all n. An in absolute value is larger than an plus 1 for all n. And the third one, limit of an is equal to 0, right? Terms are decreasing, changing signs and going to 0. Then the series is convergent. Okay, now this series is convergent means the sum is equal to a real number. So let S, which is just the sum, the limit of partial sums, is equal to this, an, Okay. So here Sn is the sum of the first n terms and partial sum, and this is the value of the sum. Sn can be thought as an approximation for the sum, right? We may think of Sn as an approximation or estimate for the real number S. The error in this approximation is how much? Well, the error is this. This is the actual value. This is the approximate value. Error is the difference in absolute value, right? So the error is this. The fact is this. We can estimate this error. How much error you make when you take Sn as your estimation. Değil mi? You make some error, but what is the magnitude of error? The fact is this. S minus Sn is less than, in absolute value, the first term you ignored. Right? You take summation up to An and you leave An plus 1 and the rest outside. That error is less than the first term you ignored. Okay? Why is that? Proof is very easy. Uh, what is S minus Sn? Well, S is the sum of all of them. This is the sum of terms from 1 to n. So if you subtract the first n terms, you have n plus 1 and then n plus 2, right? N plus 3 and goes like this. Okay. Now, what do we know? I claim that this gadget in absolute value is, so S minus Sn is equal to An plus 1 plus An minus plus 2 in absolute value. Well, I can write it this way. Uh, you see, this is An plus 1 plus An plus 2, An plus 3, An plus 4, An plus 5, and so on, right? Uh, Note that each An is either positive or negative. For simplicity, let us assume that this is a positive number. If it is negative, let's multiply everything by minus 1. In the absolute value sign, if you multiply all of them with minus 1, nothing changes. Therefore, there is no harm assuming that An plus 1 is positive. But if this is positive, then we know that this is negative. And this is positive. And moreover, in absolute value, this is larger than, no, yes, this is larger than this one, right? This is like this, 1 plus, it's like this, right? This is negative, this is positive, but this is bigger in magnitude. Therefore, this is a negative number. Similarly, this is a negative number. And actually, all of them are negative numbers. So this whole thing is a negative number. The first one is a positive number. However, I can write it this way also. An plus 1 plus An plus 2 plus An plus 3, sorry, plus An plus 4, and so on. And this time you see what? This was positive, this was negative, but this was bigger in magnitude. So this is positive. This is positive. Each term is positive. So this means what? This infinite sum is positive. The first term is positive, and the sum of all the rest is negative. Right? All the rest is negative. Yani şu var elinizde. So you have a positive number. You add to this a negative number. So this is positive, this is negative, but the sum is still positive. This means what? This means that absolute value of A is larger than absolute value of B, and of course larger than absolute value of A plus B because B is negative, right? So we have exactly that situation. Uh, A plus this expression is positive, right? A plus this expression is positive. A is positive, but this expression is negative. This implies that an plus 1 in absolute value is larger than this whole thing. An plus 1, an plus 2, an plus 3, an plus 4, and so on. So this is nothing but S minus Sn. Tamam mı? Alright, let's stop here. Next time I'll do more examples related to Taylor series, and we will also make use of this estimation to make some approximations. Alright, let me stop.